Thank you. Thank you to the organizers for selecting my talk. So my name is Sandra Wiersma, and I'm a postdoc in Christine Joblin's group at IRAP. But as you can see from this rather busy title slide, my work is part of a larger collaboration under the banner of the Nanocosmos Synergy. So I made one kind of laboratory analog, and in the ICMM group in Spain, in the group of Jose Gago, they made another kind of analog. And we also discuss all of our results with the group of Pepe Canicharo at the in Spain. So I would like to start by talking to you today about how this dust is formed. So for this, we are particularly interested in circumstellar environments, and in particular those around carbon-rich dying red giant stars, where there is a lot of sooty chemistry. But this is not only carbon-rich soot. What's also prominent in these kinds of environments is a very strong silicon carbide dust band. And for silicon carbide dust, how this dust is formed is not entirely well known. Several different candidates as molecular precursors have been suggested, because different ones have already been detected. But thus far, more laboratory insight would definitely be necessary. And I'm going to try to tie this silicon dust story to the already well-known to you probably polycyclic aromatic hydrocarbon story. So as we all know, the aromatic infrared bands are ubiquitous. And there are two different approaches to look at how these PAHs got into the interstellar medium, either through bottom-up mechanisms, so taking small molecules, for instance, those in this rich sooty chemistry in circumstellar environments, or top-down mechanisms, so on grains from graphite flakes, having these PAHs come off of them. So these outflows of sea-rich red giants, they are often proposed as a way to bring these PAHs into the ISM finally, but PAHs themselves haven't been found in these circumstellar shells. So there seems to be a missing link if this is how we get them into the ISM. So that's where laboratory simulations have an important role to play. Currently, laboratory simulations for how this dust is formed are often done under relatively high densities, even though the densities in circumstellar shells are comparatively low. And the chemical diversity is also lacking, so often no silicon is included. The group in Madrid, Gago's group, has used carbon and hydrogen, and carbon and C2H2 in a relatively low density experiment, and they showed efficient carbon cluster formation, but no PAH formation, at least not efficiently. However, research by the group of Peter Saar has shown that crystalline silicon carbide, both in its alpha and beta variant, can catalyze C2H2 into PAHs at relatively elevated temperatures. At the end of Peter Saar's experiment, the silicon carbide often ended up graphitized, which is interesting because in another work by Gago's group, they showed that PAHs can be etched off of graphitized silicon carbide using H2. So this begs the question, what is the molecular content that is associated with the formation of organosilicon dust? So for this, we've used two different methods to form silicon carbide dust, or organosilicon dust, I should say, so that we can analyze these different analogs and find out which mechanisms are most likely to occur. And I'll start with the machine in Madrid, the Stardust setup. So as you can see here on this slide, this setup is really quite large, using a dust source and several different analysis stations, all under UHV. And I won't be going into all of these details today. So today I'm going to focus primarily on the source. And later I'll talk a little bit about the temperature programmed desorption experiment. So this sputtering gas aggregation source that they use to produce dust uses a 150 SCCM argon flow focused on 3 different independent magnetrons, of which we've used 2 for our research, one of polycrystalline silicon, another one made of graphite. And the argon around these magnetrons engage in a certain trap and release flow mechanism, which allows more complex molecules to be formed. And later, all of these materials will also aggregate together in this aggregation zone, where they are also allowed to react with a laterally injected flow of reactants, in our case, hydrogen up to 1 SCCMs. Those formed species are then deposited on gold or gold-coated targets for in situ experiments with the TPD, or ex situ experiments where we do high-resolution mass spectrometry on them. The machine I made the laboratory analogs on was the Pyrenea 2 setup at IRAP. So this machine is also going to be used for a lot of other experiments, but today I will be focusing primarily on the source and the laboratory Stardust analogs that we make with it. But here we use 2 rotating rods made of different materials, one of carbon, one of silicon, and focus a green ND YAG laser on them. As this happens, a plasma plume is formed, and as you can see in this configuration, both plasma plumes mix with one another. And then by pulsing helium gas with a backing pressure of 2 bars through this plasma, we encourage collisional cooling and the formation of clusters. And this beam then supersonically expands, and we can analyze it online using a quadrupole mass spectrometer, or again, deposit the material on a gold-coated target for ex situ analysis. And we add our reactants, such as C2H2 or H2, in the helium pulse directly. So moving on to our mass spectrometry results. So for Stardust, we started with TPD, temperature programmed desorption mass spectrometry, sputtered silicon and carbon together with 1 SCCMs of hydrogen. And we deposited this on solid gold and mounted it on a heatable surface and positioned a residual gas analyzer over top. As you can see here, as the temperature goes up, we end up detecting mostly relatively small hydrocarbons in this series. And the largest hydrocarbon that we find here is C10H8, showing us that with this method, we're detecting no more than 2 aromatic cycles. But a sample that we deposited on a gold-coated substrate was also used for aroma analysis back at IRAP. So we only needed a thin layer for this, and then we use infrared light for a relatively soft kind of desorption, and a UV laser to ionize our species. And this gives us an atomal detection limit for aromatics. And using this orthogonal time of flight mass spectrometer, we have a mass resolution that is sufficient for us to be able to tell nanosilicon species and hydrocarbon species. So this is what such mass spectra would look like, but I'll just go through it quickly for the sake of time. At low mass here, what we find is that we have primarily silicon species, both oxidized and not oxidized, and we have different kinds of small HC clusters. And at higher mass, when we don't add hydrogen, so what we see up top, we have carbon clusters dominating our mass spectrum. When we add hydrogen at both of these flows, we find that aromatics start to pop up at relatively typical intervals. So for more detail, we can look at our hydrocarbon content only and plot the hydrogen versus the carbon content. And as you can see, we have these different regimes. So on the bottom, we have our carbon clusters. And in between here, we have hydrogenated carbon clusters. Between the blue and the gray, we have our aromatic molecules. And on this line here, we find our so-called typical PAHs, pericondensed sp2 hybridized molecules. So without adding hydrogen, carbon clusters clearly end up dominating our mass spectrum, as we saw already. But when we add H2, we find for both of these that C16H10 dominates, which are the small yellow dots that you see here in the middle. And we see some sort of tendency towards this pericondensed range. We can also split this out into different families. So what you see here is that when we have just the silicon and the carbon, we make a relatively small amount of aromatics in total. But once we add H2, the carbon cluster count is strongly diminished. And we see mostly a large increase in the formation of different organosilicon species. And we see a significant uptick in the amount of aromatics that are formed. Also notable is that between these two rather different flows, the intensities are rather comparable, suggesting that we have a plateau. Moving on to the Pyrenea 2 setup, where we use a different method to make our stardust analogues. So this is the online quadrupole mass spectrometry. So we ablate just the silicon rod for this example here and add a varying percentage of C2H2. So adding only the helium, we see silicon clusters, but adding C2H2, even at a very low flow like this here, we find that a series pops up, taking this form of silicon with different with larger and larger amounts of C2H2 added to it, and this series becomes larger the more C2H2 you add, and this is reminiscent of the formation of polyacetylenic chains. And what's interesting is that it doesn't matter which source of silicon we use. So using different rods or combinations of rods in this machine, you get a very different result when you only use helium as our carrier gas, but adding C2H2 forms very similar mass spectra, showing us how reactive this silicon is, no matter in which shape we add it. So I will also take a look at this H to C diagram for silicon plus C2H2 again. And what we find here is that we find very few things outside of this aromatic range. So finding the carbon clusters and the HC clusters, you need to add carbon in its atomic form for that. Again, though, we find C16H10 to be dominant and another aromatic species on this line as well. Looking at the different families using different rods and rod combinations, we find some interesting trends. Looking at just a carbon rod, we find a large amount of carbon clusters, but also a rather big amount of aromatics. When we add the H2, we strongly diminish our amount of C clusters, and we don't see a large change in the amount of aromatics that's formed. Adding C2H2 does create a lot of aromatics suddenly and keeps the carbon cluster count low still. When we add silicon to our carbon, not adding any extra gases, we find that we don't diminish our carbon cluster count that much, but we do create significantly more aromatics. And when we use only the silicon and the C2H2, most of what we form is just aromatics. So now how to address these changing molecular families under these increased chemical complexities. So for that, we have to go back to some of the works that have been done before. So for stardust, we know that when we add the carbon plus the hydrogen, we mostly make carbon clusters and not that many aromatics. When we add C2H2, some aromatics are formed, but it's not a spectacular amount. So for Pyrenea 2, immediately adding just carbon and hydrogen, we know that we start off making a lot of aromatics, likely due to the high pressure and the temperature that we deal with there. Adding the C2H2 does boost the amount of aromatics that we form, but not as drastically as when we add the C2H2, where it's significantly increased. For stardust, we find that, as I just showed, with H2, no aromatics, a little bit of aromatics with the C2H2, but then bam, when we add the silicon and the carbon together with the hydrogen, we more than double our relative amount of aromatics formed, even though we're not adding C2H2 in this situation. And another interesting fact to note is that when we look at the specific molecules that are formed, for both of these, in the end, C16H10 is the dominant PAH here. So to conclude, large fractions of aromatics are formed in Pyrenea too, and stardust forms significantly smaller fractions of aromatics. So this is likely due to temperature and pressure differences. The addition of silicon in the end increases the formation of PAHs regardless of which temperature and pressure conditions we have. And also in all of these situations, C16H10 is preferentially produced. So with that, I'd like to thank you for your attention.